All right, so today we're going to be going through a little bit of lab work. We'll be collecting some data today. We have the essential question posed: how can we compare and contrast two different laboratory methods for determining the acceleration due to gravity? We also call that local g, lowercase g. Okay, it's local to the gravity field sort of that we're in. So this is going to be a measurement of Earth's gravity field because that's the planet that we're on right now. The known value, the literature value, is 9.8 meters per second squared. So if we're doing calculations and we can accept the fact that people have done this experiment before with better apparatus than we've got at our disposal today, more sophisticated apparatus, we have better conclusions. And so 9.8 is sort of like the known value. In this course, you should always use 9.81 meters per second squared for G. 9.81, all right? And depending on how good the lab is, we might get close to that. We might, get not too close to it. I've seen answers, all over the place, when we've done this before. But if we're sort of mindful of doing the lab correctly, then we should sort of get something close to 9.8. All right, that tells us how quickly things accelerate here on planet Earth under the influence of gravity. So every second something falls in Earth's gravity field, it goes 9.8 meters per second faster. So the change in velocity is 9.8 meters per second of time. So 9.8 meters per second, or 9.8 meters per second squared. We're going to determine this experimentally with the drop lab and with the pendulum lab. So the drop lab, we're going to vary the height that we're allowing an object to fall, and we're going to time how long it takes to fall that distance. It should maybe make intuitive sense to you that the higher up something is, the more time it's going to take to fall. Okay, so we can kind of use the relationship between those things. This actually comes from one of the equations of motion that we took a look at deriving yesterday. A displacement that is vertical, we call height. And as long as we drop it, so we have a mechanism where we're just sort of drop the marble, we're not going to throw it down with any initial velocity. The first term goes away, the initial velocity times time, and it's just the accelerated sort of term, 1/2 gt squared. So again, as we kind of work more with the equations of motion, we'll see sort of where this really comes from. For today, we can just accept it as true. The height is related to the time something falls according to the gravity field via that equation. So theory suggests that to be true. If it is true, we can take measurements of h and t and determine g. So we're trying to determine g, right? So those unknown. Same thing here, the pendulum lab. We have theory suggesting that the time t that it takes the pendulum to oscillate to and fro, back and forth, is equal to 2 times pi times the square root of max. No one likes the radical there. How long the string is divided by the gravity field. So this L here stands for the length of the pendulum string, which again will be able to sort of vary. So any good science experiment says, as I vary this, I will measure something else. As we vary the height, we will measure the time. As we vary the length, we will measure the time. Okay? Again, should make kind of intuitive sense that the stronger the gravity field is going to affect the times for these things. So, how strongly will gravity sort of accelerate sort of a pendulum that's moved up in the gravity field. All right. So I'm going to kind of this a little bit. All right, let's think about sort of organizing this. All right, is there any preference as to which one we do first? We have a strong opinion about what we should sort of do first here, the pendulum lab or the drop lab? The drop lab first. All right. So the drop lab is based on the equation. The height is equal to 1/2 the gravity field strength times time squared. Okay, theory suggests this. You're going to write a CER tomorrow. even by the end of class today. And your reasoning statement is going to begin, because theory suggests h equals 1 half gt squared, I can determine g by, and you're going to kind of walk through this, kind of what we did again. The independent variable, that's the thing that we control, and that's going to be the height. And so think a data table where height measured in meters, we're going to vary that. As we vary height, we will measure the time that it takes the marble to fall this height. We'll do that with photo gate timers to make it more accurate. Okay, we'll measure that in seconds. The theory suggests that the height is related to the time squared. Okay, so if we're measuring t, but we're really interested in t squared, let's add a column in our data table for that. And so this will be a calculated value. Whatever number we get here, we're going to times it by itself, square it, and we'll record that here. And I think that's pretty good for a data table. We'll just use basically those. And then we think about analysis. Okay, and this is really where students should try to work on the skill of looking at an equation, thinking about what's measurable. What can I vary? What can I measure here? How can I reach a conclusion? And it's always going to be like with a line. Okay, we're always going to try to sort of force the data into a linear relationship so that we can find the slope of it. Set the slope equal to what it should be. So if we think about this as like y equals mx. Okay, equation of the line from math class. Let's change this. H equals 1 half g t squared. So y equals mx. Like we learned in math class. Equation of the line. If we plot y against x, there's a trend. The slope, right, is m. Here, this is physics class. All right, and these are not just arbitrary variables that are meaningless. They stand for things in reality. Okay, like we actually do things in physics class, not like math class. So there's, why is Sarah buying 115 dozen strawberries? Because we got to subtract it from 20 dozen, something like that. Only in a math book, you can get away with buying it. So anyway, we're getting away from the point here. We're going to plot h on the y-axis. Measured in meters, always being sure to label our axes with quantity and unit, because I will take 0.5. And then let's plot that against t squared measured in seconds squared. And now everybody's going to get mad at me. They're like, hey, wait a minute. I thought in science we plot the independent variable on the x-axis. Here you are plotting the dependent variable on the x-axis. I know. There's no rule that says we have to. And the reason why I'm choosing to plot the independent variable on the y-axis is because look at the equation. It's like y equals mx. I could rewrite the equation and make it like t squared equals 2h over g. That's the same thing as this. Okay, it's like multiply both sides by 2, get rid of that. Divide both sides by g, you have this. So then you could plot like y equals mx. Y equals mx. Here's the point. We can decide. Okay, it's up to us as the sort of scientists doing the analysis. Say, well, I always like to plot the dependent variable, right? At the time depends on the type. Okay. And it is true that we tend to plot the dependent variable on the y-axis. So you have to sort of manipulate the equation a bit, but put it like this, and then you just plot the t squared on the y against the h's on the x, and your slope will be equal to 2 over g, 12 over g. I prefer we do it this way, not being so rigid in our thinking that we can't just plot the independent variable on the y-axis. I mean, like I said, there's no rule that says you have to. You just deal with the equation as it is now. So the way it's written here, we're going to plot this on the y-axis, and we're going to have a set of ordered pairs of x and y, where this is our x coordinate, and this quantity here is our y coordinate. So if we do that, then we're going to have y equals mx. So it's like t squared is the thing we're plotting on the x-axis. H is what we're plotting on the y-axis. And our slope, we can then set equal to 1/2 g. So again, you can either decide to apply this against that, and your slope should equal to 2/g, or you can plot h against t squared, and your slope will be equal to 1/2. Either way, we're going to solve for g. All right. So what I'm saying here is that we're going to fill in this data table, and we're going to find that indeed, as the height increases, the time squared also increases. We're going to get 1, 2, 3, 4, 5, 6, 7 data points. We're going to draw a best fit line that represents the turn of the dot. Once we plotted it, we will then find 2 points that are more than half the page away from each other, that we can read off what their coordinates are because they perfectly intersect the gridding of our graph. Right? So we have to sort of scour our graph to find those points. But these are good points here because they're not data points, they're on my best fit line, and most importantly, I can read what their coordinates are. Being able to do that allows me to calculate the slope. Okay, so in terms of our x's and y's now, the second y minus the first y, the rise over the run. The difference in the y's is the rise, the difference in the x's is the run, the rise over the run is the slope. So we'll just have coordinates that we can use slope formula, find the slope. The slope then gets set equal to 1/2 g. So like your graph is really an analytical tool. It's not just a display of your data. Okay, so it's like, here's the data I collected for you to look at. It's like, I'm using this now to do some analysis. This is telling me how gravity affects things on this planet. So I can use this as an analytical tool to deduce what the relationship is between height and time squared. I get a number for this, right? Like slope equals some number. Let's say it's 4. 4 equals 1/2 g. That's very solvable at that point, right? You just multiply both sides, and solve for g. That's your conclusion. G equals some number. Look what the units will be when you take the slope of this. Meters per second squared. Those are the right units for acceleration. So setting it up this way also sort of you avoid the trouble of, like see how g is in the denominator over here? So if you plotted it this way, you set your, the slope equal to 2/g, but the units would be second squared over meters. Well, it still is correct, right? Because g is now in the denominator. So you still get the right units no matter how you do it, as long as you sort of subtract it. I think maybe this whole bit over here was very confusing. Okay, I wish I would have even said it. It's like, this is what we're doing. If all this was confusing, don't worry about it. Just forget I said anything. If it's like, I get it, that makes sense to me. Awesome. Feel free to, have the freedom to plot it how you want to. The idea is that like we can do algebra to this and we can make it, this. T squared equals 2h/g. That's a perfectly valid equation. We're just sort of pulling out that h is our independent variable, right? So that's the thing I'm plotting. Is like h is x. T squared is y, so everything else has to be the slope. This tells us how, like, what number do we multiply a height by to determine the time squared? What number do we multiply the time squared by to get the height? Okay, the same relationship. All right, so here's what we need to do. That's an apparatus here. And this is where I actually did have the projector. So I'm going to see what this looks like here. All right, so I want to show you at least the setup for this. So we've got our apparatus to determine the time that it takes something to drop. So this little mechanism here, the catch is spring loaded, so I'm going to put the marble in there. And we want to sort of drop it, so that's like a way to sort of drop it every time. And we want it to basically be 0 initial velocity. So I want to start to measure the time right when it falls. Okay, basically when its velocity is 0. And then I'm going to be able to vary the height. I'm going to drop at the same height every time. How I'm varying it is like, well, I'm varying where I'm measuring it between. So what I'm actually going to sort of vary with this is the placement of the second photo. The idea is here, as the marble falls through, like between these two photo gates, these will record the time. And then the time to fall this height. And then as I vary this, right, it's going to take more and more time to sort of fall through. Right, so I'm going to vary the height really just by varying the position of this photo. I'll just make sure the marble falls clean through. This one's first, and so we want it to go first here. This one's second. This is like we're going to pick up my wires crossed. Make sure that you don't have and stuff here. So this one goes like this. Well, consider miss. Will it work today? What about it is not working? Well, that one's good, I think. That one's good. Or that's good. This one here. Makes me think it wasn't a cord at all. It was this thing. Today, tomorrow, this will be done. So there's no rhyme or reason to it. There's no laws of physics that govern the working of the photo gate. That's magic. This is the physics of dropping of the market. So the photo gates can really give you three pieces of data wired up correctly when it's all functioning properly. It'll tell you like the time it took to pass through one photo gate, the time it took the marble to break the other photo gate, and also give you the time between the two of them, which is really what we want. They both have to be sort of functioning in order to get them. So all of this is down here. Okay. I always suggest to take the time up front to like really make sure your apparatus is set up correctly, because then the data collection is very forthcoming. It's better to like, take the time up front to do all that correctly than to like struggle with all the data collection. So we've done that. All right, we've got our apparatus set up here. I'm going to start to collect data. So I'm going to fill in this data table right here. All right, and then we're kind of clean this up. Still getting our plot of H, measured in meters, the height, right, from the photo gate against the time squared. Okay, and we expect a trend. And we can draw a best fit line through the trend in our data, find 2 points, find the slope, and then set the slope equal to 1 times g to solve for g. G will be your conclusion. The claim you're going to make based on this data, the acceleration due to gravity is whatever. All right, so we got our marble here. You can see the photo gate displayed as I drop the marble through. 0.0997 seconds to fall through the photo gate. That's when the photo gauge, for a distance of 8.8 centimeters apart. So for 8.8 centimeters, that's 0.088 meters. And it took a time of 0.909. Here I am last week telling you to take those 5 meters up to fall for a second. So almost a second right there. 0.0997 seconds. Everybody with a calculator knows that t squared is leave behind in class. Everybody with a calculator knows that t squared is I can get my calculator. Oh, why not get his calculator now? I'm all in trouble. All right, everybody with a calculator knows that 0.0997 squared is. That 0.00994. 009. Okay. So remember, these are the quantities we're going to plot. Right, this is what we're actually going to plot. Okay? T squared against H. It might be worth a repeated trial for that. What can happen is if the marble sort of veers off course, so we're relying on the entire sort of marble breaking the plane of the photo, the sort of beam there, and it sort of veers off course, only with sort of a sliver of it breaks the photo, then it's going to well, I don't know if that would affect because we're measuring between the two of them, but if it happens with one of them, like remember when we measured the width of the marble to get the velocity there, so then that was affected. But here, I don't any piece of it touches it, it's just getting the time things up. That's critical for this one. All right, so now we're gonna vary our independent variable here. Always a cause for great celebration in the physics lab. And that is exactly 21.6 centimeters. Note I'm being as precise as the instrument allows me to be. So it's 21.6 to 0.216 meters. I didn't just say, it's like 0.2. I'd say 21 and a half. Yeah, it's like 0.6, not 0.5. So be as precise as the instrument allows me to be. How long does it take a marble on Earth to fall 21.6 centimeters? That's the question on everybody's mind right now. Well, let's figure it out. How many people thought 0.174 seconds? Good hypothesis. 0.1748 seconds. 0.1748 seconds. That's how long it took something to fall 21.6 centimeters here on Earth. But my theory is telling me how the time squared goes with the change of height, right? So I like T is what I can measure, that's time. I can calculate the time squared. That's just going to be 0.17481 squared, and everybody knows what that is 0.03056, let's say. Okay. Would it be 0.03055? The next number is a 5, right? So let's round this up to 6. And then be consistent, like we talked about, like just keeping the same sort of consistency here, since I've recorded like what's out the millionth places, thousands, and so the 100,000th place. All right. So keep that same consistency. You're right, in my calculator, this is like 504, right? But since we're sort of stopping at this place, round it correctly. We want 7 data points, and you see like the data will just fall where you know, in the place we're going to plot it. You can be mindful of like, I want to vary it 5 centimeters exactly every time, or whatever. It really doesn't matter. There. We're just getting 7 here. Now we've got 33.2. Which is 0.332 meters. How long does it take something to fall? 33.2 centimeters here on it. 0.2238 seconds. 0.2238 seconds. As soon as you've established a trend in this level of your academic career, high school physics, because things don't always like the trend continues forever, right? Like things can have a earlier trend, go up at certain places and go back down and back up and crazy. But here it's like everything is aligned without exception. And as soon as you establish that, like as you increase H, these numbers are increasing too. Any violation of that trend you should be really suspicious of. So like, oh, wait a minute, I don't trust that data point to be collected again. You know, so you should be somewhat mindful of like what the data is going to look like when you go to plot it, and think like, hey, maybe I should go back if like I only have 6 data points, but I'm down here. Maybe I should go back and get a value like something like 15 centimeters or something. Maybe be somewhat mindful of that. And then if I did that, I would expect the value between these two, right? Because the data should sort of fall into alignment. All right. What is 0.2238 squared? Who's already got that? 0.05009. Yep. Think about how you're going to have to scale this axis to plot these values. Right? Like each square is going to have to be like 0.00 something, right? So you can spread that out. We're probably not going to even be able to you know, account for how precise it is. So we could almost kind of like just round it to like 1,000th place. You know what I mean? We'll just call this like 0.010, 0.031. We should maybe round this to the 1,000th place. Because I mean, how are you even plot that 0.009? Like, oh, it's this much further over on my little square here. You know, it's kind of like a high thing. Deal with that. There in the independent variable. There's little islets here where the laser beams are actually going through. So like this photogate itself has thickness, and so we'll draw measure from the top to the bottom, from the top. You know, the important thing is consistency. However you decided to measure it, be consistent in all your measurements so that you don't sort of, well, this time I'll adopt this procedure and the next time some other way. That won't affect my result. But in physics, we tend to think, from the center to the center. So like the center of the thing being measured, like what's the distance between the sun and the earth? Well, it kind of depends. For gravity, the center of those things makes sense, but it's like, well, the light reaches the surface of the earth and the surface of the sun, so it sometimes depends on it. And then you're making a judgment about where the center of that thing is. I'm making a judgment about sort of where does this line match up with the center of this thing. All those judgments introduce uncertainty, error into our results that we as scientists want to be honest about and account for. This is 47.5 exactly. So 0.475. Again, that's my judgment. Somebody else might look at that and go, not like 47.6. Somebody else might say that's like 47.4. There's maybe like plus or minus a millimeter of uncertainty in that measurement. Okay, so just kind of keep that in mind. 0.2760. 0.276 squared. 0.07618. Again, we're seeing a nice trend, right? Just like you would expect to. 4 data points. $58.4. 0.584 meters. So that's moving half a meter now from here to here. So it's gone out of the field of view of the camera. And those following along on YouTube. 0.309. 0.3090, right? To be consistent with sort of the same number of digits there. 0.309 squared. Everybody got it? Good. I heard somebody type it down in the comments there on YouTube. 0.09548. I can hear into the future. All right. Well done, whatever it was. All right, let's look at another one. We got ourselves 64.5. It is possible to like perfectly land on an alpha, sitting in your normal weight gun. So if it is there, call it that, but you don't just round it there if it's close, right? You precise things allows you to be. It does get a little bit more uncertain. Like, are we going to make it through the sort of bullseye here every time? The further down we go. So I think we need one more data point after this one. We might be kind of at the max here for what we can do. So that's 0.3272. And everybody would calculate as a 0.3272 squared is 0.10706. Did I not do that? The right number? 0.10706. The way we are right now, we want to round to that place. And again, I very much doubt we'll be able to sort of account for how precise it is after we go plot it. So we're probably just end up plotting 0.009, 0.03, 0.05, 8, like 8. This would be 0.1, this would be 0.11. You know what I mean? But we can always deal with that later. All right. Should we go back and try to like fill in one right here? Let's go try to like put this thing exactly at 15 centimeters. So if I say like here's exactly 15 centimeters right here. Oh my God. right here. 15 centimeters. 0.15. 0.145. Remeasure, sure. 0.145. So it's right in between these two. Okay, even though I wrote it down here. When you go to plot it, it won't fall where it belongs, right? It doesn't matter what order you plot this data in, but if you're plotting it correctly, this one will fall in between these points. We can expect a time now between 0.09 and 0.176. Right, like if this physics holds, when I drop this thing here, I should see a number in this guy that is between those first two entries, 0.0994 and 0.03. When I want it squared. So 0.0997, 0.17, right? I should see the value. One, 3, 7, 4. In the physics hold. See how that does indeed 0.1374. It fits right where it kind of should, right? Like if we pick a height between these two, it should be a time between these two. Indeed it is. When we square it, 0.1374 squared, we get 0.01888, okay? Which indeed is in between 0.009 and 0.03. Right? So this way, if we say, well, there's going to be like a lot of space between the two data points, we've got to sort of fill it in and select a data point. So now we've got 1, 2, 3, 4, 5, 6, 7 data points. Tomorrow, some, coming here. Oh, for the e-learners, we'll talk about sort of, that by the end of the class, okay? But it's the same time, work on your analysis, okay? You're going to plot H against T squared like a set of ordered pairs. So if I think about like X's and Y's, ordered pairs, this is my X, this is my Y. That's 1 point on the graph, right? And then I'll plot another point. Go over that far on the X-axis, go that high up on the Y-axis. That's another point. I'll have 7 points. 1, 2, 3, 4, 5, 6, 7. And sure enough, there'll be a trend like this because we can see that as we've made this quantity, as this quantity has gotten bigger, so does this one. But as we made the height bigger, the time squared got bigger too. So there's a trend like this. Find 2 points that are not these points. Do not calculate with these numbers. You're slow. Don't say, oh, the difference in the y's is going to be like this minus that. The difference in the x's is this minus this. And what was the point of collecting all the other 5 data points? See this? So the trend line is more accurate than any 2 data points. The moment you draw a trend line which represents the trend in the data, that's the most accurate thing on that graph. Not more accurate than any 2 data points. Yes, I'll do my thing. Like, sure. Lisa, to check out. Well, what about the drop or the pendulum lab? Check YouTube. Or get the data, more importantly, tomorrow, just ask your colleagues for the data so that you don't get public on. But it'll be posted, it'll update Instagram, I'll post it. So don't use data points to calculate the slope. Calculate the slope with points that you can read off what their coordinates are because you scaled your axes. Okay, like you scaled that axis accordingly. So you can just see like, oh, these 2 points look, they're right on where the squares on my graph paper intersect. So it's easy to read off what their coordinates are. And then you do, the difference in the h's over the difference in the 2 squares, that's the slope. The slope is equal to 1/2 g. So the graph will give you a number for slope. Slope equals some number. That number, theory suggests, should be 1/2 g. Whatever the time is, for something to fall squared, multiply it by 1/2, multiply it by the acceleration of gravity, the theory predicts how high up that is. So we're sort of leveraging our knowledge of that theory to say, well, I can measure these things, and I'll calculate what g is. I will determine the acceleration due to gravity. So that's one lap. Let's do another lap. We're on a roll. Now, we're on a roll with the first week's lap, right? Physics. We're on a roll. Now, we're in the swing of things. Oh, I'm sorry, but that's about as funny as it gets here in this lab. Nothing. All right, let's get into the swing of things here with our pendulum lab. For this one, there's only two things that affect how long this pendulum takes to oscillate. Two things. One thing is how long the string is. The other thing is how strong the gravity field is. Doesn't matter how much mass is on the end of it. I mean, according to this theory, the only things that affect the period of oscillation are how long the string is and the gravity field. So like if there's a stronger or weaker gravity field, if there's a longer or shorter string, those will be the things that will affect the time of oscillation. That's what theory predicts. That's what you will say in your reasoning statement. Because theory suggests the time that it takes the pendulum to oscillate, which is the period of oscillation, is equal to 2 pi root L over G, I can vary L, measure T, plot a graph, same kind of a thing. We're just going to have a little bit trickier mathematics here because of that radical. How can we take care of that radical? Who's got some algebra thoughts on this? Move over to this part of the board. Pendulum view here. Who's got some thoughts on what we can do with this? Anybody? What don't you like? You love pi. No, you're a pi. I like pi so much. Like kind of a natural square pi. How do we get pi squared? Is everybody okay with this, like squaring everything in this? Are we good with that? Are we allowed to do that in algebra? You just square everything because you want to? Yeah, you can actually. That's allowed. As long as you square everything, the same equation. But it has to be effective, like the square root of anything squared is itself. And so the whole point of squaring, everything is to square this term. If we square the square root of L over G, then it's just L over G. And I'd rather look at that than like radical. I don't want to work on any radical. I'd rather work with that. So now instead of working with this equation, I've got T squared equal to 4 pi squared times L over G. And let's rewrite that slightly. T squared equals 4 pi squared over G times L. That's the same thing as that. Okay, this is all just like algebraic manipulation. We haven't changed the equation. Theory suggests T equals 2 pi root L over G, or T squared equals 4 pi squared over G L. Same exact equation, just a little bit of algebraic manipulation. But now you see what we've got, y equals mx. So I could plot T squared on the y-axis this time. The last time I plotted on the x-axis. This time it makes sense to plot it on the y-axis. Like this equation of a line is like, hey, the variable that's all by itself equals this other variable over here, and then this is just a number that captures like how they're related. For example, if you did the circle out, go measure a bunch of circumferences of a bunch of circles. Go measure their diameters and do this experiment. Plot the values you measure for circumference against the values you measure for diameter, and you'll find that there's a trend between how big a circle is across and how much distance around it. Okay? If you were to take the slope of the best fit line for this experiment where you've actually measured these things, you find circles in nature, your eyes judge this looks like a circle, there's its diameter. Measuring the circumference is a little bit trickier, but like you could put a string around it and pull it straight. You could put a ruler up to it a bunch of times and sort of go around, sort of marking off each centimeter. You would find that I could get any diameter, even when I didn't even measure, and multiply it by the slope of your best fit line, and it would predict what the circumference is. In other words, there's a rule to circles. Circles are 3.14 times further around than they are across. That's what sort of one of the ways that pi shows up in nature. So that's the whole point. Like there is, science is after the capturing how things in nature are related. And we'll find all sorts of relationships in nature. We'll find that, like when we study electricity, like, oh, the voltage and the current are related. The resistance is related to the power. You know, lots of things have these relationships. And the slope just kind of tells you what you need to do to this quantity to get the other one. Okay? And so, like going back to the drop lab, all we were doing there was saying, okay, if something falls from a certain height, I know I'm in this gravity field, I can predict how long it's going to take according to this equation. Or whatever the time is squared of something falling, multiply it by this term, 1/2 g, and that can predict the height. Okay, so the relationship between how high up something is and how long it's going to take to fall to Earth squared is related by this term 1/2 g. Here, the theory predicts that the length of the pendulum string multiplied by this mess, 4 pi squared over g, just some number, right? Some number will give us the time of oscillation squared. Time of oscillation is to and fro. An oscillation is there and back. And that seems a little bit worse than the original one, but it's actually easier to deal with. So when we go to do our analysis tomorrow, we're going to have a data table with values for t squared, measured in seconds squared. We're going to have values for length, measured in meters. And see how g, our conclusion, is in the denominator? The units of our slope, when we go to calculate the slope, are going to be in seconds squared per meters, like rise over run. But we'll take the inverse of it when we go to solve for g. So we'll still get meters per second squared. In other words, you're going to get a number for your conclusion for g. G equals, you're solving for local g. You're determining, like if you are, I'm in a foreign gravity field and I need to know how strong the gravity is here to get my spaceship off this planet. Let me take off my shoelaces and do a little pendulum experiment here, and I will deduce the gravity field on it. Let me drop some marbles and find it. I can figure out the gravity field on it. So G is our conclusion, the claim that you're making, and it'll be in meters per second squared. So let's go ahead and just do the same thing. 7 data points, you find the slope, but now the slope you'll have to set equal to 4 pi squared over g. So the analysis for this experiment, the first one that you can, well, this is the one I said, don't worry about it so much. If you plot it this way, this is y and this is x, then your slope would be 2 over g. And then you kind of have like, hey, for both ones, I can plot t squared on y-axis, but it's not required. Okay. For the graph where you're plotting height against t squared like this, your slope is going to be equal to 1/2 g. I have to really emphasize here that you determine the slope just like with the way that you learn how to math plot. Remember, and you're solving for g, right? But g is the unknown thing you're trying to determine as per the simplified. All right. We're measuring other things in order to deduce g. Even though I told you at the beginning of class, like it has a known value of 9.8. Don't feel like you have to get that number or you did it wrong. You get 8. Hey, that's pretty close to 9. Get 10. That's really close to 9.8. Okay. So don't, I mean, I just want you to be honest. Whatever it is, even if you get something that is wildly incorrect, like you get 980 something, well, it's like, well, it should be 9.8. Then you get like 980, it's like, oh, you plotted centimeters instead of meters. So there's some order of 10 here. So sometimes it's like you can see where the mistake is by looking like, oh no, you were right. You just have to move the decimal point. You plotted centimeters. So just be honest, whatever it is, I don't feel like it has to be. I will force my slope to be this, so that when I calculate it, and it doesn't match it out. All right, let's collect some data here on this pendulum. 11:15. Okay, so what we need to do is think about the idea of uncertainty that we have here. Like, I was in judgments about the heights. Well, we're going to time this, and if I am interested in the period of one oscillation, let me make this a lower height so that we can see it. If I make this a height like this, and I'm curious about the time of oscillation, a single sort of oscillation, I get my stopwatch ready, and I say, start, stop, time of one oscillation. A lot of what I'm measuring is just how long it took me to push the button. Okay, it's much better, even though I only want it at the time of one oscillation, it's much better to adopt a procedure like where I time, like maybe start my stopwatch. Now, count 1, 2, 3, count 10 oscillations, time 10 of them. And so my data table might look something like, I'm going to vary L in meters. I'm going to vary the length of my pendulum string in meters. I'm going to time 10 oscillations. Okay, so I'm going to time 10 oscillations. That'll be in seconds. And then I don't really care about 10 oscillations. I'm only doing that because I'm spreading out my human reaction time, pushing a stopwatch over a greater measured value. Right? And so if I time a single oscillation, my measurement is dominated by human reaction time. But if human reaction time is absolute, in other words, it's the same human reaction time when I start and stop the stopwatch, then I could time 100 oscillations in between. Well, I mean 100, the bell's going to ring, so we'll just do 10. Okay. But I really just want to know T, the time of one oscillation. So hopefully you as a student sort of paying attention right now will say, okay, well, if we're timing 10 of them, but this is just the time of one, I know what to do to get from here to here. I'll know what to do with this number to report my answer here. And if it's not clear, just keep paying attention. We don't want to know T. I mean, we do. What we really want to know is T squared, right? Because that's what we're going to plot. So this is the suggested data table. Independent variable, this is the dependent variable, and these will be calculated values. Like this is what we're actually going to measure, and we calculate what we're interested in from it, and get better conclusions by adopting a procedure where we spread out our human reaction time over a greater measured value. To make the experiment even stronger, we could time at each length several times and average them, right? But in the interest of that T up there, that time, we don't want to do that. We'll just trust our first measurement and recognize that, hey, if we really need to get a better conclusion here, we could adopt a stronger procedure. So we're going to start out at 31.4 centimeters, which is 0.314 meters. So note how I'm reading my ruler in centimeters. But I'm just automatically converting it into meters when I write it down. If you plot it in centimeters, then your answer is going to be like G in centimeters per second squared. Okay, we want meters per second squared. So I'd rather just like do it in the beauty of the metric system is it's all base 10, right? 100 centimeters a meter. So if I measured 31.4 centimeters, that's just an easy divide by 100 and use a decimal point over 2 places. Now let's time some oscillations. Everybody with a stopwatch, who wants to collect their own time data, can certainly do that. If you want to just trust the data that I will publish up here for my measurements, you can do that also. If you're following along at home or on YouTube, feel free to pause the video and time it more precisely than where we'll get here. Time signature in the video. It doesn't matter which 10 oscillations you time. I mean, it kind of does. Like we're just like this thing go forever. Eventually, the wind is going to sort of slow its motion, and we're not really accounting for that. But it's not like I need to start my stopwatch upon release. I could let it go for a bit and then say, okay, I'm going to start counting 1, 2, 3. So I get 10 oscillations as 11.20 seconds. You can have your own stopwatch out. Again, you can still be timing this any 10 oscillations. Okay. If it took 11.2 seconds for 10 oscillations, then it took 1.12 seconds for 1 oscillation. So I just divide this by 10, right? I just say, hey, that's 10 oscillations. We're assuming that each oscillation is the same amount of time. So just divide this by 10 or move the decimal point over one place. That's why I chose 10 instead of 5 or something. Because then you just do the math like this. And then 1.12 squared. I did that in my head also. Let me just see here. 1.12 squared. That's going to be 1.244, I think. I use the calculator for that. 1.2544 according to my mental math. Let's check on the calculator. Yep. Happen to have that in the display. All right. Now we're going to vary the independent variable. There we go. Okay. It might take 1.12 seconds for a pendulum to oscillate when it's 31.4 centimeters long. Or how about when it's 41.3? 41.3 centimeters is 0.413 meters. Oh, great. 41.9. 41.9. One. I got 12.96 seconds, which is 1.296 seconds. I added a 0 there for consistency's sake. 1.296 squared in my head is 1.679616. 1.6796. We'll round that down to 6 there. And again, I don't think we'll be able to show sort of the precision of these, 10,000th place, but if you want to round this when you go to plot it to the more manageable place value, that's fine. All right, vary the independent variable. Now we're going to be oscillating with a pendulum length of 49.1. Oh, 0.419, 0.491. How about that? Now, hold on a second. So wait, you're not being very consistent. It's like with sometimes you're releasing it from here, sometimes you're releasing it from here. Here's the thing, it doesn't matter. All that matters is the length and the gravity field if that theory is correct. If I displace it a little bit, it doesn't go so fast. I haven't given it as much potential energy to convert into kinetic energy. It also has less distance to travel. If I give it more potential energy, it will go faster, but also has to cover more distance. And those things perfectly cancel out such that, I mean, as long as you have, we are using what's called small angle approximation for this. Like if I were to do this, look what happens to the string. You got like it's slack in it. Oh, that changes everything. So as long as I like just a somewhat, sort of small angle here, I'm not releasing from like up here, it really doesn't matter like where I choose to sort of release. Okay, because if it's it's a greater angular displacement, faster to move up to the sort of slower, smaller distance. Those things are always perfect. That's 12.65. Remember what I said, as soon as you establish a trend, you need to be suspicious about any violation of it. So the fact I got 12.96 here, and I just got a little bit less than that. I mean, I didn't vary that much, but it's noticeably longer, measurably longer. I should get a longer period. I'm gonna test it again, and if I don't, I'm gonna go back and check my 41.9 again. Maybe that's where the spurious data point came into play here. That's why you have to be, collecting your own time data here. You say like, oh yeah, you only counted 9 off. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14.01. That's more like it. I'm going to do that. Maybe I'll just count it. 14.01, 1.401, right? So make sure we have to find a single oscillation, not 10 of them. For 1.401 squared, I'm getting 1.9628. Okay, there we go. Vary up this independent variable a bit. $60.6. So 60.6 is 0.606 meters. Fifteen point six one, 1.561, and 1.561 squared is 2.4367. 2.4367. 4 data points. 5 here. Give us like 3 more data points here. Or may have after this one. We'll calculate. All right, we got 0.7 2. 72 centimeters, 0.72, put that 0 on there for consistency's sake. Two, 3, 4, 5, 6, 7, 8, 9, 10. I'm getting 16.67 seconds. Pop quiz. What is the time of one oscillation? What is the time squared? We have however much time it takes me the conversation to answer that.
Discuss the
Maybe after this class someday.
Actually,
I'm out tomorrow.
after class, after second period, I can do anything
After second period, let's aim for Friday. All right, this Friday after second period. Let's do that.
So,
One second, 1, 2. All right, pop quiz over. How long did it take for one oscillation?
1.6.
You didn't give everybody else a chance to answer. It was like, I don't think too. All right, that's the easy one. How about the hard one? What's 1.667 squared? No calculators. I'm just kidding. I'm just kidding. That means to stand it out in a multiplication. All right, I'll raise you. 1.667 squared. Come on, we need to write it down. All right. We're not raising. Say again.
2.7789.
2.7789. 1, 2, 3, 4, 5. 2 more. All right, so this is as long as I can make this pendulum string. Just off the camera screen now. We got ourselves 0.823. 0.823 meters of string length. That is oscillating. One. $17.88. 1.788 squared. 3.1969. All right. Suggestions, where should we go back and get our last data point from? And we have a spot where they're like, yeah, I want to test one lower than 31, or let's get one like in the 50s.
In between like 0.5.
Somewhere around like higher than the point, that means basically 0.5, like 0.55 or something like that, like in here. Okay, so let's go for like 55 centimeters. Let's try to force our, hey, we're in control of the independent variable. All right? That's the one we're in control of. Let's see how close. 0.550. 0.550. You guys still see that? Maybe? A bit floppy there. All right. If physics holds oscillations is to be between 14.01 and 15.61 seconds. Like we would expect that because this theory, I mean, we've noticed that as we've made this longer, it's been taking longer to oscillate, right? And so if we pick a point like in between here, which we have, we'll have it set up, we should get a time in between there, just like we saw with that other one. So let's see what we do. One, two, three, 4, 5, 6, 7, 8, 9, 10. 14.83. How about that? 14.83 is higher than 14.01, is lower than 15.61. 1.483 squared. 2.1993. 2.1993. All right, so there you can see both of the data collected, both of the data tables that you can sort of fill out in your journal. You can follow along, pause the video right now, and copy all those numbers down. Hopefully the focus stays clear enough for you to do that. As a quick recap and as some instruction for what you're going to be working on tomorrow, let's remind ourselves that for the pendulum, data, I encourage you all to plot time squared, which will be measured in seconds squared on the y-axis against the length measured in meters on the x-axis. Plot your 7 data points. Let me do this. When you plot your 7 data points, you're going to see that they roughly fall into a trend line. Won't be perfect. There'll be a little bit of scatter. That scatter represents the uncertainty in the measurements, but there'll be a noticeable trend line that you decide, use your judgment to say, this is my trend line. Never connect the dots. Then you've got 7 lines. You need one single line you can find a slope of. I'm not using data points. I'm finding points that are on my vested line. Intercepted reading on my graph paper, so I can do a slope calculation. I'll leave it to your sort of memories of math class to remember the difference in the y values, the difference in these quantities is the rise, the difference in these values is the run, the rise over the run is the slope. So the slope is some number which you will set equal to 4 pi squared over t. Theory suggests the slope of this graph is equal to 4 pi squared over t. Once you get this far in your lab work, hopefully by tomorrow, number equals numbers over unknown. It's just a solvable algebra problem. Multiply both sides by g, divide both sides by slope. So really, if you wanted to sort of write this down, once you know the slope, which is 4 pi squared over your slope, that's what you do. Okay? So that's how you'll deduce g. That's your claim. G equals some number, meters per second squared. Evidence, see graph. Reasoning, because theory suggests the time of oscillation of the pendulum is equal to 2 pi times the square root of L over G, or because theory suggests the time squared is equal to 4 pi squared times L over G, I can vary the length of the pendulum, I can measure how long it takes to oscillate, I can plot a graph, find the slope of the vested line, basically just re-explaining what you just done there. That's the pendulum. For this data over here, remember we're using this equation as our theory. So we're plotting the way I suggested h on the y-axis against t squared. You can see that. H against t squared. Okay. So you're plotting all these values on the x-axis, all these values on the y-axis, same thing. Find, plot all the data, draw a vested line, find 2 points that are not data points, that are on the trend line, find the slope. The the slope should be equal to y equals mx, right? So the slope will equal 1/2 g for this. Right? Like once you know the slope, you just set that number equal to 1/2 g. G is your unknown, so let's multiply both sides by 2. So 2 times the slope should be g. The way that, the way we work with the data here. Right? Just multiply both sides by 2 and solve. And then you'll be able to compare them. Guess what? We did these experiments in the same gravity field right here on Earth. So we should get roughly the same answer. Or maybe say, we know the literature value is 9.8, right? So you can maybe compare it to that and say, well, this one gave us, closer answers to the known value, but I still feel better about this because I like it. I feel better maybe. So you can kind of compare those. I'll show you how we can sort of quantify that comparison when I come back on Thursday. Okay. This has all been recorded. I'm going to pause. I'm going to stop the video now. I'm going to upload that on our YouTube channel. So tomorrow you're like, well, we're supposed to have questions. Take a look on YouTube video. Read, watch the data collection, the explanations. And we'll see you next time.